Hello, Chemistry of Earth and Space Science. We're going to continue on with our Unit 3 Dangerous Compounds lessons. This one is still a part of Lesson 1, and it is called the periodic patterns, or another word that gets fancy is periodicity. So if we look at periodic patterns, what we're going to do is we're going to look at different patterns using the periodic table that are going to allow us to predict atomic radius, ionization energy, after we define what that is, the electron affinity, after we describe what that is, and then the electronegativity. So we're going to take those four properties of elements on the periodic table, and we're going to see how the periodic table is laid out in such a way to be able to predict changes in those properties. We're going to look at each one of them independently, individually, and hopefully be able to come to consensus. The other piece of this is we really do want to be able to understand why these patterns exist. So if there's something to take out of this lesson, it's to be able to not only know how the property changes, but more importantly, why it changes. So why in the world do you think scientists look for patterns? Why don't you pause the video for a second and think about that? Well, a generally accepted reason why scientists look for patterns is the ability to take and find and predict about things we don't know. So we look at patterns to understand the relationships. So for instance, here, if we're talking about atomic radius, the relationship of atomic radius as it relates to where the elements are, how they're structured, so that later on we can make those predictions like Mendeleev was doing with the periodic table earlier. And also it's a way to take and put things in a little better sense when we're looking at very, very complex information. We're going to be looking at four patterns, four properties individually. So the other reason is when we find patterns, it's a fundamental part. We're going to allow us to formulate hypotheses, develop theories, establish scientific laws, all that interesting stuff that goes along with just being able to say, hey, there's a pattern. Recognizing patterns is one of the seven cross-cutting concepts that you see in our room of different scientific concepts to say these are ones that are very, very important. In science, patterns are important. So let's look for some patterns. Your homework associated with this is just labeled as periodic trends practice. So there are a lot of different atomic characteristics that show a very predictable trends, and we're going to study atomic radius, ionization energy, electronegativity, and electron affinity. That "and" is in the wrong spot. So what are the two properties that actually allow us to predict or allow us to understand why these properties occur? Well, the two of them, one of them is called effective nuclear charge. Effective nuclear charge, if you look at an atom and you have the ability to recognize that the nucleus of the atom is positively charged. When the nucleus of the atom is positively charged, it is going to have an attraction for the electrons that are surrounding it. So all those electrons are attracted to the nucleus. One other thing to consider is between the outer shell electrons, which is the one that's driving all these patterns, and the nucleus is a bunch of inner shell electrons. And those inner shell electrons are going to be pushing back on the electrons that are on the outside shell. So that's what's referred to as the electron as a shielding or electron shielding. So if we take and think about all these atoms and we compare two things. One, we're going to look for the effective nuclear charge, how far away the electrons are from the nucleus and how strong the nucleus is, meaning how many positive charges or protons does the nucleus have. So for each term, we're going to do that. Here we go. First one, atomic radius. What is atomic radius? Well, it is officially defined as the distance from the center of the atom to the outermost energy level of the atom. So it's like the radius of each one of these circles. Now, how do we measure that? Since we can't really measure the distance from the nucleus to the edge, is we take the distance between two touching atoms, and we cut that distance between the two centers of those two atoms and divide it by 2. And that would give us the radius. So how does atomic radius change? Well, if I look at the periodic table, one thing I'm going to notice is as I go down a column, those periods represent the shells that a atom has. So the first period has 1 shell, the second period has 2 shells, the third period has 3 shells, and so on and so forth. So as there are more shells, those electrons are further away from the nucleus, hence making the atom larger or have a larger atomic radius. So if you go down a column, that's obvious because you're going to have more and more shells. You're going to have a greater and greater distance from the nucleus to the outermost shell, larger atomic radius as you move down a column. But what's most interesting, I believe, is the period pattern. So as you go from left to right across the periodic table, you have the same number of shells, but as you go from left to right, the nucleus is getting stronger and stronger as it gains more protons. And when the nucleus gets stronger and stronger and pulls those outer shell electrons harder, that makes them come closer to the actual nucleus of the atom, making it, whereas you go left to right, even though they are going to be getting heavier, they are actually going to be getting smaller. So going up top to bottom on a column, they're going to get bigger. Going from left to right on a period, they're going to get smaller. And the reasons for that are those same 2 patterns. So if I look at it from a group standpoint, as I increase the radius, meaning going down the periodic table, is because the shielding is greater. There's more shells. The more shells, the further away they are from the nucleus, you're going to have a greater atomic radius. And as you go across, that's a decrease in the radius. That as you go across, the electrons are going to be added to the same energy level, but the nucleus is going to get more and more protons, making it a much stronger pull on the outer shell electrons. If I wanted to simplify it, I'd say that as I go from left to right across the periodic table, the atomic radius is going to go down. As I go from top to bottom in the periodic table, the atomic radius is going to go up. So the next 3 properties are going to incorporate this shells in size that we talk about with atomic radius, but we're still going to go back to those same 2 principles. Effective nuclear charge, how many protons are in the nucleus, and the shielding, how many shells does the atom have. So the next property we're going to discuss is called ionization energy. And we've already seen this one other time when we talked about the ionizing radiation. Ionizing means to remove an electron from an atom. So if I look at a element, say lithium, and I hit it with some ionizing radiation, it would remove 1 electron. And then when I hit it with more ionizing radiation, one of these 2 electrons get taken away, and you leave it with just 1. So what do you think is going to happen if I look at the periodic table going from top to bottom? What do you think is going to happen to the amount of energy that's needed to bump off an electron? So if the ability or the energy is needed to bump off an electron correlates to the strength of this attraction between this electron and this nucleus, this attraction, as this attraction gets stronger, it's going to take a whole lot more energy to remove that outside electron. As this energy between the electron and the nucleus gets smaller, that means it's going to take less energy to pluck off or remove an electron from the atom. So what happens on a periodic table? So as you go down the periodic table's column, going from top to bottom down a column, in general, the ionization energy decreases. Why is that? It's because as you go from top to bottom, there's more shells. Those electrons are further away from the nucleus, so they are much easier to remove from the atom than those that are closer to the nucleus. As you go from left to right on the periodic table, the period pattern, it's actually going to increase. And that's because as you go from left to right, they're on the same shell. They're basically the same size. If nothing else, it's going to get smaller. So those electrons are going to get closer to the nucleus, and the nucleus is going to get stronger and stronger. So the amount of energy required to pluck off or to remove that electron is very, very large. So the why is ionization energy and atomic radius are inversely related to one another, meaning the smaller the atom, the more tightly the electrons are held to the positive nuclear charge. Next property that is actually very, very much associated with bonding, actually ionization energy is too, but when you're talking about a real bond, electronegativity is this ability or the inconsistent amount of sharing of the electrons that are shared between the two atoms. So here's a hydrogen fluorine molecule, and hydrogen fluoride is the name of the molecule. And if you just look at it in general, you can see that fluorine has 8 electrons around it, and hydrogen has 2. So those 2 that are shared here in the middle, those 2 electrons are the electrons that represent the bond that holds together the hydrogen and the fluorine. Well, hydrogen has just 1 proton in its nucleus, and fluorine has 9. So already fluorine has more positives. Yes, it is a little bit bigger, you can see that, but fluorine has more positives. And because fluorine has more positives, has literally 9 times as many positives in the nucleus, fluorine pulls the hardest when it comes to pulling electrons that are part of a bond to it. So here's a cute little illustration where you have the hydrogen with its little weak, wimpy arms trying to hold on to those electrons that are being shared, and fluorine is pulling very, very hard and pulling electrons where they spend a whole lot more time around fluorine than they do buzzing around hydrogen. What that means is that the 2 electrons that are shared are going to spend a lot more time around fluorine because fluorine has a higher electronegativity. It has a stronger pull on the electrons that are shared. Here's another way it's represented. You'll see this symbol here. It's called a delta plus and a delta minus. You'll see these get used much more in the very last unit of this very last lesson of this unit when you talk about molecular geometry and polarity. Hydrogen fluoride is very polar because there's a very uneven distribution of the electrons in this atom. So why do we have this change? Well, from top to bottom, you're going to see that there's going to be a decrease in the electronegativity. That's because as you go from top to bottom, the atoms get larger. They get larger because they have more shells. If they have more shells and they're larger, that means the electrons are not as strongly held by the nucleus. So less strongly held by the nucleus in a bond, they will be less pulled towards the nucleus of the atom as you go down. As opposed to the periodic pattern, as you go from left to right, you'll notice that the electronegativity goes up. And that's because 2 things. 1, there's more protons, and 2, that outside shell is getting closer and closer and closer because it has a smaller atomic radius as you go across. So if those electrons in the outside shell are closer and the nucleus has more protons, that's going to have a much, much stronger pull on those electrons. Fluorine is going to be crazy good at pulling electrons towards itself, whereas these guys over here, not so much. Now, the one thing I should say, electronegativity is only when it's a part of a bond, more specifically, and again, plant this seed of a term, and is part of a covalent bond. Then last pattern to worry about is the electron affinity. So ionization energy is the ability to pluck off an electron from a atom. Electron affinity is the opposite, is that if I were to add an electron to an atom, electron were to go from being free to going to be a part of an atom, when it does that, some energy is going to be released. And the stronger the attraction of the electron to the atom, the greater the amount of energy that's going to be released. So if electron affinity is the amount of energy released when an electron is added to a neutral atom to form a negatively charged ion, as you go from left to right, because there's going to be a stronger attraction because it has more protons, you're going to have an increase in electron affinity. As you go from top to bottom, you're going to have a decrease in electron affinity. So let's just say that these four patterns all revolve around the same thing. As you go from top to bottom on the periodic table, you're going to have an increase in the number of shells. It means you're going to have a weaker attraction of the electrons towards the nucleus, and that will lead to a bigger atomic radius, a weaker ionization energy, a weaker electronegativity, and a weaker electron affinity. And as you go from left to right on the periodic table, you're going to lead to a similar size shell, maybe even one that's getting smaller because the atomic radius is decreasing, but it has more protons in the nucleus, leading to a smaller atomic radius because it's pulled in tighter. A larger ionization energy, it requires more energy to pull off that electron from the outside shell. A greater electronegativity, when they are part of a bond, the atoms are going to pull harder on the electrons in the outermost shell that are part of bonding. And finally, electron affinity, when the nucleus is larger and the radius of the atom is smaller, then you're going to get a larger and larger amount of energy that gets released as you add an electron to that atom. Therefore, the electron affinity will increase. Okay, so that's everything about the electron affinity. In your homework packet, there is a handout revolving around the around the periodic patterns. Lesson number 2's video will be coming very soon. Have a fantastic day. Toodles.